Okay, here's our next problem. Some sort of bizarre contraption, but let's analyze what's going on. So the thing starts from rest. So right away we know T1 is 0. Obviously, in the chapter we're in, we're going to be using energy, so let's just know we're going there. So that would imply initial kinetic energy 0. And when we look at this device in this configuration, okay, notice this angle is 45, and that's theta. We should kind of mark that down. Given this statement, theta equals 45, so that's the theta we're talking about. We're told this spring here at the bottom is unstretched. So in the current position, the spring potential energy is 0. The system is still, and so somebody has their hand on it or something so it doesn't just go. I have two 3-foot long 15-pound bars from A to B, pinned from B to C. And BC comes down and connects to this wheel. The wheel weighs 20 pounds. It has a radius of 1 foot. So what's going to happen is, as somebody kind of has their hand or their foot in the way, and they remove that, and then this wheel will start rolling out. Okay, rolling without slipping, just rolling its way out, and then these things will just come, rotate down, and they'll eventually flatten out, and the momentum would take them, farther down. Okay, so we have to analyze this thing. So the question is what is omega AB? Here's AB when theta equals 0. So when this thing gets down level with the spring, what's the rotation angular velocity here? All right. So we've got a lot of parts. So let's just start breaking this down. T1, obviously 0. The question we're being asked, here's position, here's velocity. It's an energy problem, so we can just go with that right there. Next thing we need to do is take a look at V1. So we'll just start knocking that off. So, as we said, this is unstretched, so the spring's doing nothing. 1/4 times 4 times the stretch, 0. Bam, done. Or compression would be in here. Either way, 0. So now, this roller, it's a mass, but it's not changing height, so we don't have to worry about it for potential energy. So what we have here is the center of mass of these slender rods would be 1.5, along it. So 1.5 sine of 45 would be how high this one is and how high that center of mass is. We have two of them. So 2 times 15, 1.5 sine 45 describes where they are. So I'm basically taking this line here as my datum, my 0 reference for gravity-based potential energy. All right. No friction to be concerned with, no motors or other forces, so you'll notice we left out work from 1 to 2 and C. All right. So now, the next thing we have to figure out is T2, starting to think, how are we going to handle the kinetic energy here? So here's an important point. If we look at AB, it's pinned here. So AB is going to be in pure rotation, always. So we can actually, for this term, we can just use 1/2 IA, taking the mass moment of inertia at A, times omega AB squared. We don't have to do the 1/2 mvg squared plus 1/2 ig omega squared. We'll just pure rotation at A. So the mass moment of inertia at A is 1/3 ml squared. And then we'll pop that into the equation 1/2 I at A omega squared. So that's easy. All right. The spring, we know nothing about it other than its spring force. We treat that as massless, so that has no kinetic energy of concern. Now we have this wheel. All right. What is the wheel doing? Well, it's doing two things nominally. If you look, it's translating. So the center of mass of the wheel, as it goes out, is moving along a line. So you'd have 1/2 mv at c squared, and then it's rotating. So you'd have 1/2 ig omega squared. All right. So you'd have two terms, but let's think about this before we just start running off. So when these two things rotate down and get extended all the way out, all right, it's going to be rolling out, but when these things get to the point where it's straight, what's going to happen? As this continues to go like this, the wheel will start coming back. So when these are flat, this is at the farthest point it can go. It's an inflection point because it's going to now start, or pivot point, it's going to start coming back the other way. So this is important. What that says is that the velocity of this center is 0. When these things flatten out, that's it. It's at its furthest point out. It can't go any farther. It's in the process of turning around to go back the other way. VC is 0. Well, if VC is 0, then what's the angular velocity of that wheel? It's also 0. So this thing, when we get out, when this point gets out 6 feet, 3 feet plus 3 feet, has absolutely no kinetic energy. Okay? So we just got rid of that. So that's what's all right here. Everything about the wheel. So we've talked about this. We'll treat it as being at A. And we're going to now look at this piece, BC. All right? Well, oops. Let's just think what we have here. We just said that the velocity of C is 0. If the velocity of C is 0, it says that is an instant center for this AB. So it's got motion. It's coming. It's rotated down to here, and momentum would keep it going. All right. So there is an omega CB, but at this instant, since VC is 0, that's the instant center of this thing. So at this instant, CB is in pure rotation about C. Well, let's think about that even further. This is in pure rotation about A, and VB will have some velocity. When it gets down here, it'll be straight down. The velocity of B on this link is the same as the velocity of B on that link. These are equal length, and VC is 0. So this is in pure rotation about A. This is in pure rotation about C. So what is its kinetic energy for this thing? It's exactly equal to what AB is. So when I write the kinetic energy for this, I can just multiply it by 2, because what this is doing at this instant, that's doing the exact same thing. So that's what we have here. So here's T2 for AB, what we talked about, that we're taking the 1/3 ml squared, IA. And T2 for BC, well, we know that it's an instant center. BC is in pure rotation about C. And so the velocity at B is the same for both links. Therefore, omega BC equals omega AB. So T2AB equals T2BC. So all we have to, when we go to put this in the equation, we'll just multiply that term by 2. All right. So all we have left now to finish this is, well, what's V2? All right. Since we use this line here as our reference, when these bars go flat, well, they produce 0 potential energy because it's relative to what we had before. But now this is stretched, so I need to get the full stretch to go out. All right, so we have 1/2. The spring constant is 4. This will extend out to 6 feet. And this was the length when it was unstretched. So keep in mind, this is the unstretched length. That would correspond to 3 cos 45 plus 3 cos 45. That's what this distance is to start. So 2 times 3 cos 45 is the original unstretched length. So 6 minus that will give the stretch. We square that, and V2 is done. And let's bring this up. I apologize. Here we said T2AB is T2BC. And here's the second potential energy is just in the spring, 1/2 4. And this piece of these wheels going to move out to 6 feet. And this was the original unstretched length. 6 minus the original unstretched length squared is the stretch. Bam. All right. So that lets us finish this problem off, which I have right in here. So you can see the picture. So here we have V1, because T1 was 0, so we had this simply is the potential energy of these two pieces, these two bars, because the spring is unstretched, equals, I have a 2 around the T for AB. So that accounts for link AB and link BC. Plus, here's the stretch of the spring. So there's the energy in the spring from that. We have one unknown in omega AB. Solve for it. We get 4.28 radians per second. And this problem is finished. We have 3 more problems to do. We'll see you shortly.